Yeah, we will come to your doubts in a moment. All right, then let's begin the class for today. So before I get into the doubts or questions that you have, so there is an announcement. You have to submit your first assignment. Assignment 1. Okay. So I will divide all of you in a group of each group consisting of 3 members, and amongst you have to prepare, each group has to prepare a presentation on the topic of evolution of triple junction in the Northeast Pacific. Okay, so you have to prepare a presentation. So group presentation. The topic is evolution of triple junction in the Northeast Pacific. Okay, so you will find that in Laudy's book at 1.2.7.2. Here is that at page 30. Okay. Now you should not restrict yourselves only what is written in this book. You know, it depends. So it's an assignment which will be marked, of course, and evaluated. So what it means that you have to bring in more material from elsewhere, from papers and everything, you know, and make your presentation as good as possible. So what you have to do, you have to pre-record your presentation. Pre-record your presentation and share the link. I mean, you can keep it in your Google Drive and share the link with me by. So today is 18th. That means next Wednesday. Okay. So you have a week. By next Wednesday, you have to share the link with me. This will be evaluated. I will just announce the group members. And yeah, you should not spend more than 20 minutes. Okay, for the presentation. Okay, so if you are crossing 20 minutes, that means marks will be deducted. Okay, you have to restrict your video within 20 minutes. And the second condition is everyone should speak in the group. Okay, and based on the quality of your slides, the way you present, and you know, I will understand how much you have understood about the topic. I will mark you. And here are the groups. So there will be 4 groups: red, green, yellow, and blue. Red group contains Danal, Damanjit, and Pritam. Green group contains Ishita, Shushma, and Anirudh. And then yellow group contains Shreya, Naman, and Aditya. And blue group contains Prashant, Nirupa, and is it Amol or is it Bela?
Sir, it's Bela.
Bela, okay. So Bela. So you 3 will be making the blue group. So you have to prepare your presentation, and then of course pre-record the video, and you can use Google Meet and make like a meeting amongst three of you, and record that session, of course, and share the link with me by next Wednesday. The topic is same for everyone: evolution of triple junction in the Northeast Pacific. The basic reads are present in Laudy's book, as I said, in page 30. But then, of course, you have to bring in more content to it from elsewhere, from the internet, books, whatever. It's up to you. Okay. This time the group presentation is of the same topic, but next time, of course, the topics would change from one person to the other, from one group to the other. Okay, so this is your first assignment. Any question around the assignment? Something you did not understand? Shall I repeat the group once more? Danal, Damanjeet, and Pritam will be in the same group, that is red group, and then Ishita, Sushma, and Anirudh will be in green group. Shreya, Naman, and Aditya in yellow group. Prashant, Nirupa, and Bella will be in blue group. Okay? Any question around the assignment? Okay, excellent. So now let's come solving your doubts. So what is your doubt, Danal? Hello, can you speak up, Danal?
Yeah, sure, sir. So in the previous lecture,
Yeah, in the
pre-recorded lecture,
pre-recorded lecture, okay?
yeah. If can I share my screen for better understanding?
Okay. Go ahead.
You can see.
I can see your screen, yes.
Okay. So in this diagram, this
Right.
one,
Uh-huh.
this 2.8, we we draw this 2.8 at which angle?
That is perpendicular to that
AC.
the perpendicular to the trench, right?
This
Well, which one is trench here?
this is bridge. This is fault. This one is French.
Yeah,
So perpendicular to this.
right.
So this is 60.
No, that is, as I said, I explained it is oblique.
Yeah,
Uh,
it is oblique.
yeah, yeah,
If we draw a line 60 degree to perpendicular
yeah,
of north to north, so parallel to that 60 degree. Yeah, I
exactly.
got that. Okay, I'll check that later.
Anything
Okay.
else, guys?
No, no, sir.
Yes, sir.
Discuss
I have
with,
doubt in the
yeah,
AB velocity gradient line. I couldn't understand how it is in that way.
which one?
The small AB line. Yes, sir.
This one.
So small AV line should be, it should pass through A, right?
So it will pass through A. Yes, sir.
Yeah,
Uh,
and then B would
so
go towards A. And it is oblique simply because it has oblique extension. Sorry, oblique convergence. So A and B is trench, right? So the velocity line
yes,
would pass through AB. The AB small AB line would pass through the line point A, okay, and B is propagating towards A, right? In if that convergence would have been perpendicular, then small AB line and capital AB line would have been perpendicular
perpendicular.
as well. But then here, as it is an oblique convergence, as I said, most of the convergences are oblique, hence the angle is there. Understand?
Yes, sir. Yes, sir. Got it. Yeah.
Yeah. So you have to, kind of understand these. I mean, the earlier lecture and this lecture, the pre-recorded lecture and the earlier lecture together. Okay. Read the book. Have you read the book, guys? Lowry's book.
Yes, sir.
Okay, very good. And then try practicing that once, 2-3 times, and then while you do this assignment as well, the things will be even more clearer. Okay, I'm sure. Anything else, guys? Any other question that you might have on triple junction stability, or anything around plate tectonics or?
So one doubt is,
Yes.
suppose in our description we are completing the triangle, but
Right.
the third length is not coming exactly the same given in
Then
the.
the triple junction will not be stable. Otherwise, you will not be able to complete the triangle. Now, the triangle will stop somewhere. If the length is not met, it will not be a triangle, isn't it?
Yes. Yeah, means in the question if some length is given, but
Yes.
we are
So
getting some other length. So
then it means that I mean, one thing can be, if it is very little negligible, then that means you have made some very little mistake. You are measuring them with your scale and everything, right? So there must be some error which is like 0.1 centimeter if it is away. Then that it is perhaps stable. You have made some little adjustment that you have to do. Okay, but it is off by like 10 centimeter or 1 centimeter or so. Yeah, then that your triangle is not. If the triangle is not complete, period, the triple junction is not stable. Okay,
yes, sir. Yes.
but make sure that your small measurements are not is not responsible for that error. Okay, that you have to make sure.
Yes, sir.
So do this exercise if you can. If you do that, say for example, I did it very roughly on a piece of paper, right? If you do it on a graph paper, you will be even more accurate. Then you can measure all your points very precisely. You understand my point?
Yes, sir.
So if you are kind of 100% sure that you are okay with you have not made any error and all the measurements are exact, then you should be able to finish the triangle. If you can't finish the triangle, that means there is some sort of problem with your the triple junction is not stable. Now let me give you what I'm trying to say. Let me just let's say for example, I have a triangle. Okay, so this is suppose 4 centimeter. Okay, this is 3 centimeter. What would this be? This would be, if I can calculate mathematically, this will be equal to 3 square plus 4 square, right? Pythagoras algorithm. So what does it mean? 9 plus 16, that means 25 minus 5, right? Ideally, this should be 5, right? Now I can measure 3 centimeter with a scale. I can measure 4 centimeter with a scale. And if I make a little bit of mistake in measuring 4 centimeter, this will not turn out to be 5. It can be 4.9.5, You understand my point?
Yes, sir.
So you can actually cross-check whether these things are right by using some simple trigonometric equations. So if I am off by 0.1, then I know that this is stable. If I am off by 1 centimeter, then I know it's not stable. You understand my point? Yeah?
Yes, sir.
Oh, very good.
Sir,
Yes.
I have a doubt in that last problem in that pre-recorded lecture.
Yeah.
So I have drawn the parallels of the velocity vectors That means
Right.
for making the triangle AB and
Right.
BC of sides 2.8 and 2.7 centimeter respectively.
Right.
So again, for checking the CB, that means the third side length, I checked with a normal ruler. I was getting around 3 centimeter.
Okay.
So it was around 3.1. So
So that means it is stable. Yeah.
I thought it was some error in my parallel line calculation.
Yeah. Yeah.
So, but after joining CB line, it
Mm-hmm.
was not parallel to the ridge velocity vector. It was completely making an angle.
Then you might have made a mistake.
But
You
after
have not
making,
taken. You have not then taken care of the obliquity of the trench.
yeah, I took the same parallel angle, parallel for the oblique trench.
Then it should be okay.
But when I took the ridge, the parallel of the ridge, and joined the and made a new triangle, then I
Mm-hmm.
was getting the new side length was 3.4 as mentioned in the last
Right.
seniors.
Right. Yeah.
So I was
So it
getting
should
two
be
answers.
it should be the same thing, na? I mean, why would it be different?
But
Whatever way you do it.
but the length of side CA, which was 2.7 centimeter, has increased when the new side was 3.4.
Okay. I mean, there must be a little bit of adjustment that you need to do. Is that right? So
Okay.
2.8 to 2.7 centimeter. That's what you were saying?
No, not 2.7, 2.7 to something else. It was coming when I took 3.4
Okay,
triangle.
I have to see your calculations in front of me. I don't know what exactly is happening.
Actually,
Okay.
I haven't did in the graph paper. I did in normal plain paper.
Yeah,
So
just do it. Try it once more precisely in the graph paper. Okay, you will see that things will just match. Okay,
okay, sir.
try
Right.
try doing it in a graph paper and do it carefully. I'm sure it will work. Okay,
Okay, sir.
because the principles are exactly the same. Okay.
Yes, sir. Thanks.
Okay. Anything else? Yeah, Danal. Yeah, in that particular case, you remember that T was essentially perpendicular. The T had a in that RFT thing that I talked about in the previous lecture. It was not an oblique um, convergence. It was a perpendicular normal convergence, right? So that's why your F and T had to be parallel. I mean, it had to be collinear. Okay. Okay, so what I want to say that if you're so in case of in if your if you don't have an oblique convergence, okay, if you have a perpendicular convergence, in that case for an RFT triple junction, the F and T has to be collinear. Okay, but if the velocity vector is oblique in case of the trench, depending on how much oblique it is, your mutual angles will change. Okay, but in case if I have a trench which has a perpendicular convergence, the primary condition is the F and T has to be collinear. Okay, whatever the velocities are. Anything else? Okay, so I don't know how many of you, all of you are now familiar with the with the assignment that you have to do submit. Those who have joined later on, please talk to your friends I have already assigned you in groups, and I have already talked about the assignment that you have to perform and submit by next Wednesday. So please identify your group and talk to your friends, and all the best. Then let's start with a new chapter today, and we are going to talk about gravity and gravitational techniques. Now, before we actually dive into the actual topic of gravity, let us understand one important thing, and that is what we call as prospecting. What do I mean by prospecting? Can someone tell me what do I mean by prospecting? Have you heard this word, prospecting? Okay, so what do I mean by prospecting? Rather than defining it, let me explain what it is. Suppose here is my ground surface, okay? And then suppose there is a ore body which is sitting beneath. Okay. And this particular ore body, I cannot exactly see this ore body because it is beneath it is in the subsurface. This is under the surface. There are techniques by which I can understand whether it is present, I can talk about its extent and many other properties, okay? So the process by which I actually kind of find out whether there is a material in the subsurface hidden, which is of our interest, of our economic interest, and also talk about its extent, whether it is big, whether it is small, how much depth it is actually situated, okay? All these type of parameters. The process by which we do it is called prospecting. Okay. Now, prospecting can be done in two ways. One is called geophysical prospecting. And the second is, of course, geochemical prospecting. Okay. So, in case of geophysical prospecting, what we are doing essentially, we are trying to look at different physical properties of this particular ore body. Okay, different physical properties of this particular ore body, and based on those physical properties, we are trying to understand whether they're present or their extent at the depth at which they are present, etc., etc. So using geophysical technique, by understanding the physical properties, we are doing the prospecting, okay? And that is what we call as geophysical prospecting. And in case of geochemical prospecting, of course, we are looking at the chemical properties. Now, let me give you some example, okay? Say, for example, the ore body that is present here has a density of ρ2, has a gross density of ρ2, and the surrounding rocks which is present here has a density of ρ1. Okay. Now, density is a physical property of a particular body. Okay. Now, suppose if I can, with some geophysical technique, draw a graph, say for example, I take a probe, just I'm giving you an example. I'm take a probe and run some sort of experiment from point A to B. Okay. What I will observe, and then and by that process, what I'm doing, I'm measuring the density of the material that is present. Okay. So what I will observe, suppose this is row 2, this is row 1, that is because row 1 is smaller. This is row 2. What I will find that when this is X, this is A, this is B, what I will observe that I have a density curve like this. Okay. And as soon as the body is hit, okay, I get my density is elevated. Okay. And then, of course, after the ore body is done, the density again comes back. Okay. This might not reach row 2 simply because it will be an added effect of row 1 and row 2. Okay. So now what I can say that this value of row 2 somewhere here, if I draw a line, this is my regional density line. Okay. And this is actually an anomaly. Okay. This is my regional density line, and this is an anomaly. So in case of geophysical prospecting, what we try to do, we try to find out such anomalies based on several physical properties. In this particular case, what I have shown you, the property is density. Okay. It could be magnetism. Say, for example, in case of instead of density, I am plotting the net magnetization. Okay. And suppose the ore body which is here has a higher magnetization than the surrounding. Okay. Suppose this is an iron ore, so that has a higher magnetization than its surrounding. So I will find an anomaly of magnetization, okay, based on the presence of this particular material underneath. Okay. Now, how from these anomalies I can talk about its extent, the depth at which it is present, and everything, so on and so forth, depends on the technique that I am using, and we will target each of such techniques and see how they are used later on. But this is the moral of the story, that by geophysical prospecting, what you try to do, you use geophysical techniques by which you try to understand the physical properties of the subsurface, and then you try to find out anomalies from where you kind of discriminate the ore bodies or the resources, natural resources of our interest from the rest. Okay. And when you use, say, for example, chemical properties, suppose I am doing, I'm taking up soil samples, from the subsurface, okay, and analyze them in the lab. So I have taken soil samples here, and everywhere. Okay. And then I'm analyzing them in the lab, and say, for example, I'm interested in rare earth elements. Okay. And I see that around this area I have a spike in the rare earth quantity. Okay. So what it means that the rare earth or whatever is present is mixed with the soil above, and then that's why I am seeing an anomaly or a spike in the rare earth elements. Okay, and this sort of prospecting is called geochemical prospecting. Okay, if it is based on geophysical techniques and based on the physical property, we call it geophysical prospecting, and if we use the chemical properties, we call it geochemical prospecting. Okay, is that clear, guys?
Yes, sir.
Okay, so why are we interested in studying gravity then? Okay, one reason we are interested to study gravity is to, just for its academic purposes, but not so much as a geophysicist. For a geophysicist, you want to study gravity for your own purpose, for your purpose of gravitational prospecting. Okay, so you want to use this property, or the force which we call as the gravitational force, and its response on different materials that we find in nature, and try to understand where our hidden ores are. Okay, where are the materials that we can find out using gravity? Okay, so hence we are more interested in the gravitational technique, how we can use this the principles of gravity to kind of do geophysical prospecting. Okay, so that's what we are going to do. But before we do that, of course, we have to understand, or not understand. I mean, you have all read about gravity in your high school physics. So we will do some very quick, what is that called? Recap, maybe in 3-4 lectures, and then we will get into the actual gravitational prospecting. Okay, is that fine?
Yes, sir.
Okay, I'm sure you have all read gravity, isn't it? In your high school physics, is there anyone who have not studied gravity before? Okay, I would have been very surprised if someone of you said that have not studied. Anyway, so let me just begin with some, preamble, some stories of how the concept of gravity actually came into existence. Okay, so it is being said that it is one of the greatest generalization, greatest generalization of natural laws has ever postulated by human being. Okay, greatest generalization of natural laws. Yeah. So So the story goes like this, you have heard about Copernicus. Okay. In 14th century, what Copernicus first proposed, that Earth and other planets actually move around the sun. Okay, so you have your sun, and then you had elliptical or circular orbits. Till then they understood circular orbits actually. And then he said that, Copernicus said that all the planetary bodies, including the Earth, actually moves around the sun. Although it is quite, what should I say, very obvious for us. But at that time, when religion was more dominating than science, this was really a statement, and this was really something which was quite off from the conventional beliefs. Okay, so that was what was said by Copernicus. Then, in another century later, another scientist, and he was a very rich man as well. He had a private island called Tycho Brahe. what he did in his private island, he had actually put thousands of telescopes. Okay, and for 3 years, Mr. Tycho Brahe, what he did, he kept on observing the movement of the different terrestrial or extraterrestrial bodies. Okay, he observed the movement of stars. He observed the movement of different planets. And he developed a lot of data set. Okay, and then he was not like he was a very good observationalist, but he was not a very good scientist, if we say. But he kind of put the fundamental stone. He gave all that data to someone called Kepler, and Kepler looked into that data for 8 years. Okay, almost 8 years he took to actually analyze the data that was made in 3 years. Okay, and then Kepler came up with 3 of its fundamental laws of planetary motion. Okay, so what were the laws of Kepler? You all know about them, but just for making things kind of recapping them for all of us, let us just state the laws. So the first law of Kepler is the orbit of each planet is an ellipse with the sun at one of its focus. So suppose he proposed the concept of elliptical orbit, on which the planet moves. And then he said, this is the major axis of the ellipse, the minor axis of the ellipse. It will have 2 foci on its major axis. So he said the sun will be at one of the foci. Okay. The second law of Kepler is the orbital radius of a planet sweeps equal areas at equal interval of time. So suppose, let me just draw it once more. Suppose here is sun, here is the planet. Let's just do it. Here is the planet. And suppose at time delta t, the planet moves from position P1 to position P2. Okay, and then the area swept by this planet at that time delta t is this. Okay, let us say this is delta S1. Okay, now suppose the same planet is now in here. Okay, here with the same time delta t, the planet moves from P3 to P4. Okay, then suppose this area is delta S2. Okay, remember the time still remains delta t. Okay, so what Kepler's second law is, delta S1 is equals to delta S2. And the third law of Kepler was, if this is the major axis, the length is a, and the time period of this particular planet is capital T, then T square is directly proportional to a cube. Okay, this is the third law of Kepler. We will discuss about the third law of Kepler in bit more details, but for the time being, just remember this one. Okay, so that was Kepler. At the same time, at the very contemporaneous time actually, Galileo Galilei, sitting somewhere else in Europe. What he talked about was the concept of inertia. Okay, so what was the concept of inertia? The concept of inertia was essentially, if I have a moving body, okay, unless and until I, kind of force it to stop, it will keep on moving. And if I have a static body, unless and until it is put into some sort of force, external force, it will be static. And this was also taken by Isaac Newton. Yeah. And what they have said, what they have done, they have used this concept of inertia. More Newton, what he thought that, say for example, what Kepler and Copernicus has proposed, if I have this planetary body, and this is point P1 and this is point P2, okay, and this is taking like a curve, and velocity is a vector, so it means it is changing its velocity, okay, because it is changing its direction, it is changing its velocity. Okay, now what force could have actually compelled this particular planet to change its velocity? If that force would have not been there, it would have just gone through the tangent of the through the orbit and moved along the tangent of the orbit. But it is not doing that. It is essentially making an angle and rotating along the orbit. So what was that force? Okay, and that force was essentially gravity. Okay, and that is how, in a nutshell, I mean, there is a lot of stories and offshoots here and there about the story, but this is more or less how the concept of gravity came into existence. Okay, and about the fundamental law of gravity, and that is F is equals to minus G capital M small m by R square with an unit vector R, where G is the gravitational constant and G has a value of 6.754 into 10 to the power minus 11. Okay. Okay, can someone tell me quickly what would be the unit of G? Quickly, guys, do the calculation. What will be the unit of G?
Newtons per kg meter square.
Newtons per kg. Is that
Newton
right?
meter square per kg.
Meter cube?
Newton meter square per kg.
Yeah,
Yes.
do it a little more, what is that called? Simplify it a little more. Newton is a derived unit, na? Newton is a derived unit. Meter cube per kg per second square. Right?
Yes, a meter cube per kg per second.
Right. So, this value was proposed by Cavendish, yeah, in 1798. 1798. And the modern value of G is 6.74210 into 10 to the power minus 11. You can see that, Cavendish did a pretty good job in 1798. We have not gone, we are not that more precise than what he had proposed. Okay. Now, so obviously, if I just try to put it in layman's language, if I have two bodies, and this has a the first one has a mass of capital M, second one has a mass of small m. Distance between their centers is r. Then the force acting along them is expressed by this equation. Now, can someone tell me why it is minus?
It's an attractive force.
Who says that the attractive force has to be minus? Why? I want a bit more scientific answer.
So because the potential, and if we take in terms of energy, then the
No,
potential
don't get there. No. There is more fundamental answer to it.
It depends on the object which is experiencing the force.
Yeah, so
So one object can be plus gmm by r square, another can be minus gmm by r square, according to the vectors, the direction of the force.
which way the attraction goes? That attraction is this way, right?
towards the center, yeah.
Towards the center, right? From here to here. Okay. And which way the r? So it is inversely proportional to r. So r increases which direction? This direction, right? So if r goes this way, it's like, it's opposite to each other. If r moves towards this direction, so if r becomes more, the gravity becomes less. Okay, and r has a vector which is away from the center of the larger mass. Okay, hence you have a negative sign, because r becomes positive this way and r becomes smaller this way. Okay, hence the attractive force is actually regarded with a negative sign. Okay, because the increase of r and the increase of f is like opposite to each other. Okay, here the only vector, if I forget about g, here the only vector is r. Okay, now of course, so this is you all know, r is the unit vector. Okay, now suppose, so work done for moving a distance dr can be written as dw is equals to, if the force is f, dr, right? Now change in potential energy what I have written, sorry, potential energy d capital EP. Let us say EP is the potential energy and change of it is d. EP is equals to minus dw, can be written as minus fdr. Okay, now of course, I can simply think that dr is a dr can be resolved into dx, dy, and dz in the vector space, and hence I can simply write down, I can even simplify this formula, equals to fx dx plus fy dy plus fz dz. I'll explain why I have written that expression like this in a moment. Okay. Now, this Gm by r square is minus Gmm by r square is also equals to mg, right? Is exactly the same. So mg means, you know, if this is the mass of the smaller body multiplied by the gravitational acceleration. Okay, so the small m cancels out. The g becomes minus gm by r square. Of course, you can put the unit vector. Okay. Now, the unit of small g is equals to, the CGS unit of small g is centimeter per second square, right? And centimeter per second square. So 1 centimeter per second square is actually treated as 1 gal. So we will use this unit a lot. Remember that, gal. Okay. Now 1 gal is a lot of 1 centimeter per second square, or 1 gal is quite a large value for the type of business that we are about to do. Okay, so we need to kind of need to have a unit which is smaller than 1 gal. So hence we talk about milligal or mgal. That is milligal. Okay, that is 1 of 1000 gal. Okay. Now the instruments by which currently we measure this value g, we will talk about it, and that is what we call as gravimeter. Okay, gravimeter is an instrument by which you measure small g. Okay, so a traditional gravimeter has a sensitivity. A traditional gravimeter, which is, you know, analog gravimeter, I mean, which are not digitized. Okay, traditional gravimeter has a sensitivity, has a sensitivity of 1 of 10th milligal. Okay, and modern gravimeters, which are the digital version of a gravimeter, okay, they have a sensitivity of microgal. So remember this particular, in all our gravitational prospecting, what we are going to do, we are going to measure g. Okay, we are going to measure this amount small g, okay, using the instrument called gravimeter, which is based on certain principles which we will you know, talk about later on. But this is the quantity that we will be measuring. Okay, any question? Okay. I don't think you will have much questions in them, because you have already read about them a lot of times before in your high school physics. But just to, you know, all of are in the same page, that's why we are doing it. Okay. Now, gravitational potential, how gravitational potential is defined, is the potential energy of a unit mass in the field of gravitational attraction. Okay. Okay. And it is generally denoted as capital UG. So the potential energy EP will be then small m, that is the mass which is subjected in the gravitational field, multiplied by UG. Okay. So change in potential energy it is dEp will be m d ug. Okay, and remember we said dEp is equals to FDR previously. Okay, is equals to small minus small m Ag. Ag is the Ag and G are the same. Okay, I'm using Ag simply because in Lowry's book Ag is used. Okay, so that you can kind of follow the book, and this is the gravitational acceleration Ag dr. Okay, so then Ag becomes essentially minus dUg dr. This is an important equation to remember. Ag is equals to dUg dr. Now, of course, I can, kind of dr can be resolved into dx, dy, dz. So hence, I can write down Ax is equals to minus dUg dx, and Ay is equals to dUg dy, and Az is equals to dUg dz. Okay, so if dUg dr, so dUg dr then is equals to Gm by r square. So then Ug becomes minus Gm by r. Gm by r square is your Ag, and Ug is equals to Gm by r. Okay. So these are two important equations to remember as well. Okay. Gravitational acceleration Gm by r square, and gravitational potential Gm by r. So because of the time, I just stop here, and we will continue with some more well-known equations of gravity in the next class. So I think we will take, say, around 2-3 days to kind of refresh the general equations associated with gravity before we actually get into the gravitational techniques. Okay, so I stop it here. If you have any question, please ask. Okay, if not, I'll stop it here, and I'll see you tomorrow. Thank you.